So I will not come back again. So, and I hate to give you guys a test like a Monday after we haven't met for a while, so let's do it this way. The test up through the capacitor stuff, so that's chapters 18 and 19, we'll have to put all the way out till not next week, but the following Wednesday. I'll go in and I'll adjust the extra TA stuff, so it won't be due till that Tuesday night. So again, apologize for that timing on that. But next week, but the following Wednesday. So next week, because of holidays and such, we aren't going to formally meet here. With that though, so we don't start getting too far behind, we're going to push on to new stuff. So I did promise that once we got past this first rough part, that it's all fun and games from here. So we'll try and finish up the stuff for the first test today and then get to at least the start of the fun games. But you'll see a bit of a switch now that we've got a little bit of background. That from here on, there's going to be less of like lecturing stuff and a lot more hands-on things, figuring stuff out. So we're going to start on that today to make enough progress. So where we left off, looking at capacitors, let's take a look at a couple parallel plates like this. There's some wires coming in, wires coming out. And let's take a look at some details here of what's really happening. So we'll connect this to a power source, say a battery, and it's that potential difference that that battery provides, like a 12-volt battery, there's a 12-volt potential difference that provides, that pushes these charges around that circuit. In fact, specifically if you have a capacitor in there, let's take a look one by one at what happens. So let's flip a switch, connect this so we've got a complete circuit, and we'll start tracking this with time. So what happens is here comes the first charge. He comes scooting along, and there's a positive charge sitting on that plate. Well, this is a conductor here, conducting wires, and let's actually finish this off here. It's a circuit like that. So here's our little battery. So pushes a little positive charge out here. A positive charge here sees that, like charges repel, so that positive charge comes back around like this, so we get a flow of charges while that's happening, but it leaves behind this guy. But what happens with our second charge that comes along? So here's our battery, pushes another charge to the plate, but there's one already sitting there. So our next charge coming says, oh, wait a minute, there's a positive charge there, I don't like that. But this guy's kicking him in the butt and saying, so what, get on there? There's enough push from the battery to get the next one on here, and that of course pushes one off of here, we've got a negative there. The next one says, and I see two charges there that are repelling me. I'm going to need a bigger push to get on there. Next one, oh, now there's three of them. I've got to get pushed even more. So every single one that gets added on there, it's getting harder and harder to get there. I need more and more of a push.
How fast does that happen in real time?
You're going to see that later because we're going to actually do it.
Okay.
We need to talk about resistors and currents. At the tail end of our next section, we'll talk about what are called RC circuits. They have resistors and capacitors in them, and we'll be able to design the resistor and capacitor so we can essentially watch it fill, watch it dump them out. And we can adjust that. We can make it that fast, or we can stretch it way out depending on how we design our circuit. So that is coming up. Here comes another one, another one, another one. So I've got to push more, push more, push more. Eventually, I'll have enough on here that this potential difference can't push another one on there anymore. It's just, there's not enough push left to get another one on, so then we've got a filled capacitor. But what's happening with every single one on there, I've got to push more and more and more and more. Well, let's take a look at that part. If we look at the work that's done, well, let's look at it this way first. If you remember, we defined a change in potential energy as the negative of the work that's done by something. If we look at the work done by the charges, then this would be, say, the change in potential energy of each charge going on there. If instead we look at the work done by what's pushing them on there, the external work that's done, That's the opposite of the work of the actual charges themselves, so that would flip that to a positive. If you remember what this was, in terms of a potential difference, and now let's start to put some things together. If I want to know the work done by my battery to get all these charges on there and get this thing filled, the work done to get each one of them on there is different because each charge sees more and more and more on there. But, and the work done by each one of them is the charge times the potential differences across here. So notice as we're adding charges here and they're pushing charges off there, I start to build up an electric field across this gap, which means I end up with a potential difference across that gap. And of course, the more charges I can get on here, the larger that potential difference is going to be. So for an individual charge, that would be the work done to get it on, but notice that's different for every charge because every charge sees a different potential because there's other ones already on there. The way we can deal with that, though, to get the total work done, is to remember from this relationship between charge stored on a capacitor, the capacitance of that particular capacitor, and what that potential is, potential differences across them. What we can do is this, is say that the total work done to fill that guy up is the total charge that gets stored on there, so that's all of them added together, and all we have to do is then look at what was the average voltage across there as these were all filling in. Yeah, it's different for every single charge I put on there, but we can look at an average. And the reason we can get away with that is because this is a linear equation. And so it's not like some square or something like that we get a different relationship as they start to fill up. It's a linear relationship. So all we have to do is look at the average value. Here's what we can do from that is if it's the average value, because of that linear relationship, that's the same as half of the final value that we get when it's filled. In the because of this linear relationship, the average potential across that thing, if we looked at every single charge that came on, is just half of what we have just looking at our final value. Hopefully that makes some sense. Which is related then to the energy of, in this case, an electric potential energy that we've got across here. So here's where this all goes. We can figure out the energy, whichever symbols you prefer, stored on a capacitor. When it's got this much charge stored on it, here's how much energy we've just stored in that capacitor. Either this, so all we have to know is how much charge do we have on here, or what's the potential difference across here, or using this relationship, we can write this in some other terms. So since we've got that relationship, I can swap out VC for my Q, and I get another way to write this. It's 1/2 C, notice there's two V's in here now. Or I could do this, since Q is equal to VC, I can swap out, instead of for the Q, I can swap out for the V. So that gives me a 1/2 Q times a Q over C, or to write that a little bit cleaner, or if you notice where we ended up, so now let's make this nice and easy, that if we know any two of these, Q, V, or C, as long as we know any two of them, we can figure out how much energy is stored on that capacitor. So whatever two are the most convenient for a problem, as long as we've got two of them, we can use some form of this to figure out how much energy got stored on there. Couple quick things about this. One is some practical applications of this kind of thing, of storing energy, and where you've actually seen this before. And this even gets back to the question that was asked earlier about how long does this take, that we'll give more detail later. Here's a place you definitely see capacitors, is on flashes and cameras. So you know there's batteries in cameras. The potential difference across those batteries is not enough to make that lamp flash. So instead what they do is they take that current out of those batteries, send it to a capacitor, build up that capacitor until it's got enough energy stored. Then if we can quickly dump that energy, that can get enough to make that light flash. Do you ever notice though, that for most cameras you can't just go flash, 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 flash? Do you know why you have to go flash and then wait? You're literally waiting for that capacitor to charge back up, to get enough energy back in it that you can then dump out and flash again. And it makes you wait for it. So again, we'll look at that timing part later, but that's one there. The next thing, this finishes this part up, is, okay, yeah, here's energy stored in a capacitor. Well, actually, where is that energy stored when you say stored in a capacitor? So here's a nice physics view of this, is it's stored in the electric field. In fact, electric fields are stored energy. And if you think about this, what you're actually doing, this is a nice pure physics version of this. So this is different than how they're trying to tell you in chemistry or biology. When you say burn gasoline, or even eat food, metabolize it, what really are you doing? How are you really getting that energy? If you think about this, let's use the metabolizing food part. You've got some chemical compounds which make a certain charge distribution. So you've got all these chemicals hooked together that distributes charge a certain way. When you metabolize that, you rearrange those charges. When you rearrange those charges, you're changing the electric field. And if you can rearrange those charges and reduce that electric field, that releases energy. That's what you use to go running around. So again, that energy is being stored in electric fields. If we change electric fields, we can access that energy. So kind of interesting to do that. So any questions to there? Okay, so just let's finish up with a couple quick examples then. Just as a reminder before I get to these examples, here's a couple quick ones just to get kind of a qualitative idea of what's going to happen. Oops. Say I've got a couple capacitors, let's make them microfarads. This way I've got a couple capacitors this way in a circuit. And I want to find out the equivalent capacitance. You're okay with that one? When they're in parallel, you just add them up. And this one, this is the harder one, so it'll go from here to here. 1 over the equivalent capacitance is 1 over one of them. That's 1 over the other one. And then you have to flip that answer upside down. But you're okay with that, right? So here's the qualitative part I want you to be able to catch. If you put identical capacitors in parallel, do you end up with something bigger or smaller than what you started with in terms of capacitance?
I'm sorry, could you repeat that?
When you have identical capacitors and you put them in a circuit in parallel, do you end up with something that's bigger or smaller than what you started with? Bigger. They add up straight together. If you have identical capacitors and you connect them in series, do you end up with something that's bigger or smaller than what you had? Smaller. So if you have an application where you need a capacitance bigger than what you have in your hands, how are you gonna connect them? Parallel will bump that number up. If you've got an application, you need an equivalent capacitance smaller than what you have in your hands. How do I get something smaller? I can connect them in series and I'll come up with something smaller. Okay? So make sure you have that part, because that'll help answer this next question. So let's say I've got this circuit. So let's have a 100-volt power source. Let's connect two capacitors. And with this setup, once I fill that capacitor, how much energy have we stored in that? That setup. So total energy stored in that circuit. So on these kind of questions, first step is to do step by step to a final equivalent capacitance. Well, we only have 2 in here, so that's not too bad. So we'll make a final equivalent capacitor. So what do we end up with? They're in parallel, so this is 30 microfarads. If this is our final equivalent capacitor, there is nothing else between our 2 terminals, so the potential difference across the capacitor has to be the same as the potential difference across our terminals. So there's nothing else in there. So we know what C is, we know what D is. And as long as we know any 2 of Q, V, and C for a capacitor, we can figure out how much energy just got stored. If I want to know about the entire circuit, then I do all that stuff for my final equivalent capacitor because that represents my whole circuit. So in this case, we don't need, we could, we've got enough information to find out how much charge got stored on there, but we're not interested in that. All we want is the energy. Then all I have to do is use the form that has the C and the V in it. Plug those numbers in. And we get this, it's a 1.5, and the units on that, since everything here is in correct international units, the units on energy are joules, and that does come out in joules. And if you're not sure about that, again, if you look at that cover sheet I gave you guys, it shows the unit conversions. You can actually convert farads and volts, and you'll see it does turn out into joules. If you want to know then how much energy is stored on each individual capacitor in the circuit, all you have to do is that little trick we did the other day of now that we have our final equivalent capacitor, we get Q, V, and C for this, then we go backwards step by step, get Q, V, and C for each of the individual ones, although ultimately only 2 of those is all we need. And you could then calculate how much of that energy got stored here, how much got stored here. So again, to know how much energy is stored in the entire circuit, get an equivalent capacitance, and find one more of the Q or the V, but you're already going to have the V. And then just plug it in, there's your energy. So here's my question, the qualitative part. If instead I take the same 2 capacitors and the same power source and connect them up this way, will I store more or less energy connected that way? And should be able to, I'll give you 10 seconds on that one. So here's what we had stored in a circuit with 2 capacitors in parallel. We use the same power source, same capacitors, we'll just connect them in series. Have I stored more or less energy in my circuit with that arrangement than this one? Yep.
It would be less.
It's less. Why less? This, I'm going to find the equivalent capacitance. without the number yet, is it gonna be bigger or smaller than that one? It's gonna, since they're in series, it's gonna drop it down. My equivalent capacitance is gonna be left. If my equivalent capacitance is less, then my energy stored is less, as long as that's the same. So that will store less. So, one last question on this. Let's say this is how I did want to hook them together, and this is how much energy I want you to store. Here's one for you. This time you don't have to go up to the boards, I'll let you stay at your tables because it won't take too long, hopefully. What kind of power source am I going to need to connect this up to store the same amount of energy as this circuit? So I'm going to connect these two in series. I want to store this much energy. What kind of battery, what kind of power source, what's the voltage I'm going to need to make that happen? Let's see what you guys come up with on that. If you're not sure what to do, a good first step is usually take your circuit, find an equivalent capacitance. Find that first. Then see if you can figure out what kind of power source do we need here to store the same amount of energy if they're connected in series. Here's an answer for you. You have to bump that voltage up quite a bit, 268. Again, maybe a little hazy at the moment, but this one is actually not that difficult. See if we can get this one. Anyone get an equivalent capacitance yet they're comfortable with? Anyone got one?
I got 4.16667. I don't think I'm not confident though.
Yep. So make sure you get this. This time we don't want this. But we do know how much energy we want to store. Did you get it?
I got 71,000, which is not right. It's 72,000.
Did you square root it?
I did not score. There we go.
Which is why you always on the test write down all your steps.
Okay.
You would not believe how many times I see that. How many times I see people drop the square or drop the square root. So, you just move over here real quick. So since we're going to be looking at things in terms of a capacitance and a voltage, a C and a V, here's how much energy is stored in terms of those two, which again, we can find a Q if we wanted it, and use some of the others. This time I know that one and this one, I'm just trying to solve for that one. So that's just rearranging like this. And put your numbers in there. Again, we know how much energy we want to store. We know what our equivalent capacitance is, and this should be 260. Any problems or questions on that? You all good there? Okay, so that actually wraps up the stuff that'll end up on on the test, that again, unfortunately won't be for a while. But I want to jump into actually the next section, which does transition nicely anyway, but this will be new stuff that won't be on this test. And that's a start of a discussion on batteries. Just so I know, how many of you know how many volts these kind are?
No, right? Well, I mean, they call them 9-volt batteries.
They call them, yeah, what are they called? 9-volt batteries, right?
So, we have 2x4s, which
Hey,
are 1.5
how many of you,
batteries,
I'm gonna ask these kinds of questions this semester. How many of you have licked these? Let me see hands up so I can tell. How many of you have licked these things?
Everybody's
I've repeatedly touched electric fences to see for sure if they shock me, but I've never licked a 9-volt battery.
Yeah.
I don't know
What
how
happens
I
when you lick
managed to
them?
not do that.
They sizzle you, don't they? So,
I've heard they taste sour.
that's not such a bad thing, by the way. If we look at batteries and what they do, what they're really doing is they're providing a potential difference. And here's kind of a nice, let me give you a couple of analogies to this. One not so good and one's a little bit better, but if I've got a mass in a gravitational field, I can give this thing potential energy by bringing it up here. If I, put that around here. Now let me go back here. If I put this thing on a ramp, I can give this thing a certain amount of potential energy. You guys can catch this for me when it comes off. I can lift this thing up, give it gravitational potential energy right here. If I let go, I can access that energy and do stuff. This thing will roll down the ramp like that and loses its kinetic energy. If I want to repeat this and keep that going over and over and over again, I've got to come back and pick it up, and I have to, an external agent, lift this thing back up and stick it here again. A little bit more abstractly, there's a certain gravitational potential at that location compared to the floor. And when I take a mass and stick it in this different gravitational potential, I've given it a certain amount of gravitational potential energy. That's an MGH, and again, if I let go, I lose that potential energy as this does something. Yep.
We've never covered gravitational potential because we need to.
Right, but it's there.
How would we do that?
The same thing we're doing here. It's just, it's a uniform field, so it's always the same distance from, or the same change from there to there. And that's where ultimately that MGH comes from, for the energy of the thing that you stuck there. But we didn't need to worry about that location in space because we always dealt with the same field. Here's the same kind of thing, but maybe a little bit better analogy for what we're going to be doing is instead of a ball on a ramp, let's actually have water flowing down a little tray here. So here's a little tray that I can dump water in. It's gonna end up being collected here. And then I'm gonna add something in here. Let's have a little paddle wheel right here. It dips down in there. And then let's take a bucket of water and pour it into here. So what happens? Well, my water has the gravitational potential energy. If I give that water a path, it will naturally seek out a lower potential energy state. That's down here. So sure enough, down the chute it goes. If I stick a little paddle wheel in here, I can actually access that energy as this thing's coming down and actually make that do something. I can make that thing spin around. If I want to keep this thing spinning though, what am I going to have to do? I'm going to have to keep pouring water in there. How am I going to do that? I'm going to have to come over here and grab another bucket full here, lift it up, let go again, down it goes. I'm going to have to grab another bucket, lift it up, let it go. But as long as we keep doing that, I can keep that thing spinning around. What we're working with is, this is essentially our battery right here. That instead of taking buckets of water, it's taking our charges, moving them from a lower potential energy state to a higher potential energy state. If I give them a pathway, I make a closed circuit, they will naturally seek out a lower potential energy state. They'll fly around that circuit. If I put something like a light bulb in that circuit, as those charges are going by, I can make that light bulb do something. I can make it light up. As long as I keep that flow of charges instead of water, that flow of charges going, I can keep that light bulb on. But that relies on something, in our case now, a battery, continually pumping these charges up to a higher potential energy state. When you have a 9-volt battery, there's a 9-volt potential difference between here and here. So if I take a charge and stick it from here to here, I can give it a Q times V worth of energy. And then if I give it a pathway, close that circuit, I can give it a route to go around. If I put things in that circuit, I can do stuff with that flow of charges or current. So today I want to talk about this part right here, the battery. How those actually make a potential difference so that they can drive these things around. Unfortunately, when you've got a circuit, there's resistance to that flow of charges, and we'll talk about resistance a little bit later in some more detail. But there's resistance to that flow of charges through there, so you have to have something pushing them through, our battery. Wasn't really until about the late 1700s that there was even the first real exploration of this stuff. There's some stuff you read about, like ancient pots and stuff that they found in caves that they think may have been old batteries, but as far as our real development of batteries that we use today, goes to about the late 1700s or so. And what was happening back then is biologists were doing these demos that I guess people thought were really cool. They'd take these dead frogs and they'd shock them and they could get the dead frog legs to twitch. So these biologists would go around doing these like demonstrations. They were simpler times back then, but people like that kind of stuff. What happened is, again, one of these, it seems like this always happens, one of these accidental discoveries in 1780. Galvani, who was more of a biologist, was getting set up for one of these frog demos. And what he did is he was, see, you guys are all from up here. Any of you ever dealt with a real bullfrog? How big are they? You can hold a bullfrog like underneath the front arms, like a good one. About here, his legs will be hitting the ground, right? They're pretty big. Anyway, he had these frogs. And he would like stick them on hooks. And specifically what he ended up doing was he was hanging them on hooks made out of bronze. And then he, as he was setting up his frogs, he hung these bronze hooks outside on an iron trellis in his garden. And he's prepping frogs and hanging them out there. And he looks out there and he's not doing anything to the frogs, but every once in a while he sees legs twitching. And somehow that he had made something happen. Now, he's a biologist, so his initial conclusion was the animal is a source of electricity. So, oh, the frogs are making electricity. That's what's making, because I don't even have to shock them. Volta was actually a big critic of Galvani's, and so Volta came along, heard about the demonstration, and thought, oh, something else is going on here. So Volta did some experiments where what he reasoned is that the key was it wasn't the frog making the electricity, there was something happening because of this accidental discovery of having two different metals involved with this frog. In this case, the hook and the trellis were different metals. And that the frog itself was really just a current detector. The frog just let you know there was some current happening. But there's something going on with these two different metals. So he started to explore that a little bit more. And what he started doing are things that apparently half of you have done before. He actually used his tongue to test things. He would take two different metals, and he'd stick them on his tongue, and you guys feel stuff when you do that, right? And you stick that 9-volt battery on you. Did somebody say they tasted something?
Well, I've heard that it's supposed to taste very sour.
I don't know if it's sour, but you get sizzled, don't you? Well, he wasn't using 9-volt batteries because they didn't have batteries back then, but he was sticking different metals on his tongue, and he could, through that feel and taste, notice that there were differences depending on which metals he was using. And he was figuring, okay, my tongue now is my current detector. So with those kinds of explorations, he came up with the very first actual working battery in right about 1800 or so. So that was our very first working battery. Here's a little bit different one, still kind of based on what Volta was doing, but a little bit different design. This is one we're actually going to do today. It looks like this. It's a very simple one where we'll have a container. We're going to fill it with some acid. And we're going to stick two different metals in here. And again, the key is that these are different metals, not the same ones. I'm going to use some colors here. Here's one. I'm going to draw these as strips, just so we can see something a little bit better. So there's one strip that's in there, and here's the other strip. In fact, what we're going to do, let me get these right here. Let's make this one copper and this one zinc. And stick them in the acids. So what's going to happen? Anyone know, by the way, at this stage? You stick like zinc in some acid. It's going to start to strip ions off. Let's see, the zinc one, a lot of you should know what comes off of there. How does zinc come off as an ion? Like zinc, is it plus or minus? Is it +1, +2, -6, or what? That's what you should know from chemistry. You should have done enough of that. Like you should have been making like zinc chloride or something like that. And you go, oh, Cl, that's -1. Zinc is, oh yeah, that's that. So it's this many chlorines are going to be on this many zincs. Remember what it was? That's coming off. If positive ions are being stripped off of that metal by the acid, what's being left behind in terms of charge? If I take positives off, what's left, charge-wise? I get negatives building up. So as I pull ions off, I start making this negative. Copper, anyone know what that is? And this does have some different ones.
It could be 2, 3.
Plus or minus.
Well, it's a metal, so it forms positive ions, right?
Yep. So what gets left behind there? I pull positive ions off that one too. And I leave negative behind. Well, if we stop at that point, I've got some negatives here that aren't too happy because I've got like charges near each other, so they certainly try and repel. And this is a metal, so it's a conductor. So yeah, they're trying to get far apart, but they're still stuck there. I could try and do this. I could try and connect these. Maybe put a little detector here, say a little light bulb. Give them a little pathway, but so far, I got nothing happening. So how is this going to actually make a current that can turn on that little light? And why is it that the metals have to be different? How is that the key? Because my picture's not quite right.
Well, it's these are submerged in acid, right? So the ions being stripped off will form metal salts.
Doesn't
in the
matter.
acid.
That part doesn't matter. That's just sitting there in the fluid.
So the fluid isn't actually chemically reacting.
It's not it's not doing anything with the current. And again, remember they have to be different metals. It's stripping positive ions off both, right? Do you suppose it's stripping them off at the same rate?
I would think not.
Not if they're
because
different, and
I
that's why you have to
believe-
have different ones.
I believe zinc is more reactive than copper.
Yep. Which means they come off faster and more in the zinc than they do in the copper. Notice they are actually both negatively charged, but who's more negatively charged? That side. So if I connect these and I've got some unhappy like charges near each other, but I've got more of them packed here than here, how can this system make itself happier? It's gonna say, well, we're worse off, let's send some charges over that way. And now look what we have, I've got a flow of charges, I should say a flow of negative charges that way. Here's where it's gonna get a little uncomfortable until you're used to this. By convention, current is in the direction positive charges are moving if they were the charge carriers, which is opposite the direction negative charge carriers are moving. We'll see later why, or how they finally figured out who was doing the moving. But when this was all set up, they assumed it was positive charges doing the moving. So if electrons are going this way right now, then we say the current, and I'm going to use the symbol I for that, is going this way. Notice that this side is the more negative side. This side is the less negative side. And so you'll actually see, even though it's really not charged that way, this will be the positive terminal of a battery. So relative to the other one. So our current will go from our positive terminal to our negative terminal, even though later we find out, oh, it's really electrons going the other way. How long will this keep going? Because this guy says, well, let's make this a better situation, but as these charges get off of that one, more ions are stripped out, so it's still back to its bad situation. So long as you can keep that chemical reaction going, you'll keep those charges flowing.
Wait, so the electrons and the current are moving in opposing directions?
The convention that we use for current is the direction it would be if it was positive charges moving, which is opposite the direction negative charges move.
Okay.
And we'll see that later. We have to get to some other stuff to see how they figure that out.
And is that a capital I?
Yep.
Okay.
So current from positive to negative terminal. And as long as we keep that reaction going, we'll keep that current flowing. Yep. Follow that okay? Makes some sense. Let's see if I have one around here. A regular old battery, like these ones, that you guys have been using, pretty much the same concept. The only difference is in the metals that they use and the part that's stripping the ions off. This is basically like this. And as long as you keep that reaction going, this will keep putting out a current. But as you know, these eventually do wear out. I think I wrote down what these were. They use zinc, which is actually in the case itself, and a carbon rod down the middle. And there's an aluminum chloride paste that's in between that's stripping the ions off. By the way, it's a little more detailed than this, but just really quickly, qualitatively, these ones that you guys are using are rechargeables. You know what's really happening in a rechargeable battery? It drives these guys back on. So this, right now, is just pulling the ions off. If you drive them back on again, you can start over. So they're just applying, you stick them in a little thing, apply a potential difference, put those ions back on, you can kind of go back and forth for a while. Couple things here while we're talking about this stuff, of how to think of this in circuits and what a battery is putting out. So a battery has a certain potential difference that you can access, and it puts out a certain amount of current. That voltage, and kind of using a water analogy, the voltage is sort of like the pressure that you have behind a water faucet that's pushing the water out. The current is that flow of the water, and that's going to be kind of determined by maybe the size of the little pipe that you're sending it through. We'll try and come back to those analogies as we look at currents and other circuits, but you can kind of think of this is the flow, this is the push part. But the two of them will tell you really how much water is coming out the end of the pipe, so to speak. In this case, what's really happening in our circuit. If you have batteries connected some different ways, and some of you may know this, but let's take a look. Here's a couple ways I can connect up batteries. Let's say I've got something I want to power up, maybe a light bulb here. And so I want to hook some batteries to it. There's one way I can hook up two batteries. So here's two batteries. And here's another way I can hook them up. So here's the thing I'm trying to power, and maybe I put my batteries in this way. So hopefully by now you know, how would you say these are connected? In series, how are these connected? In parallel. So there's batteries in series and parallel. In this case, we'll connect them to some resistor. Some current detector tells us if something's flowing or not. If I connect batteries in series, let's say I've got standard 1.5 volt batteries, and I connect two of them in series. Anyone know what you get when you connect them in series? What you essentially made? That's the same as a 3-volt battery. When you connect them in series, those voltages add up. Anyone know what happens when you connect batteries in parallel? That's right. That's still, if these were 1.5 volt batteries, this is still 1.5 volts. When they're connected in series, you can add those voltages. When you connect them in parallel, you still have, as long as they were identical, you'll have the same voltage. Well, hopefully this makes sense why you do that. Anyone know what's in your calculators, how your batteries are connected and why? Your batteries need 6 volts to run. I'm sorry, your calculators. Most of your calculators need 6 volts to be able to work. How are you going to make 6 volts out of 1.5 volt batteries? How many and connected how? Need 4 of them connected how? Take a look in the back of your calculator. You have 4 batteries for most of you? And they're alternating? But if you look really close and track how things are going, notice when they're alternating, they're really putting them in series. They just fold them back over each other like that. You've actually got 4 batteries in series to get you up to 6 volts. So
When they're, you said the voltage stays the same when they're in series, but when it works,
they add up
in
if
series
they're in
and
series.
parallel.
So why would you do this? What's that? That's right, it'll last a whole lot longer, because now half of the charge is being supplied by both of them, instead of all of the charge by this stuff. Or, you know, if it was the same, it was a single one. So you're drawing charge off of two of them, so they'll last longer.
So,
And you can, depending on how you set them up, we'll see this later too, you can actually get more current out of that. Let me just finish this real quick. Oh, I know, yeah, this is the other thing I was gonna say. You know those 9-volt batteries you all have been looking, that half of you have been looking? Do you know how you get 9 volts? I was even surprised by this. How'd you get 6 volts by here? Took a standard 1.5 volt batteries and connected 4 of them in series, but to make it manageable, they flipped them back and forth. By the way, your regular old standard flashlights that need like 2 to 4 batteries, you know how those are connected? Those you drop right on top of each other, that's in series. So if you got 6 volts out of 4 of them in series, you know how you can get 9 volts? How'd you guys get 6 volts in your calculators? 4 in series. How do you get 9 volts? 6 in series would give you 9, right? Believe it or not, I'll pass this around. There's 6 little 1.5 volt batteries in there. That's all we are.
Or just a bunch of batteries wrapped, oh my god.
Yeah, take a look at it. I fried the bottom off of one. It's like, oh, you gotta be kidding me. What's that? Oh, I did. I wanted to see what was in there. Sure, I've licked those things before. I also opened them up. That's all those are. So here's what we're going to do to finish up today. For some it'll be pretty quick, some of it may take a little longer, but we'll have plenty of time here today. Is we're going to make some batteries. What I'd like you to do is I've got enough for 2 batteries per table, but let's see, you guys can do just 1 here. So we got plenty of stuff here. What you need is each group's going to make 2 batteries, and so each one of these is going to be a little cell. So what you'll need are 2 of them, and you'll need 2 different metals. So you'll see some copper rods in here. The other metal is in the other little thing here. These are galvanized nails. Anybody know what galvanized nails are? You've heard that, right?
well, I do know that if you try and weld galvanized metal, it'll kill you.
Yeah, so what are they? They're zinc-coated nails. So that's going to give us our zinc. So we're going to make that guy right there. So what we'll do is, what works well, you can read, I've got directions here. There's some tape here. If you put, probably with this kind of tape, you might need 2 strips across the top. That way you can poke a couple holes, stick the nail and the little rod down in there, and it'll hold them for you. Here's our acid. Got some vinegar. So that's our acid source. This will be a little holder. We'll need to figure out what we've just made. So to do that, I'm going to have you grab these kits also. And the part we're going to take out of here, to get started, is a voltmeter. How many of you know how to use a voltmeter? So we've got a couple people who do. So you're going to find out how these things work. And to do that, if you can grab a battery, there's one, out of the kit and test the voltage. These are a little bit different than standard ones. If you look on the side of this, it'll say 1.2 volts. I tried to juice them up. They may go as high as 1.3, but it should be somewhere between 1.2 and 1.3 volts. See if you can get that to say that on here so you know how to read this and know when you're using these little prongers, which side you put on the positive terminal, which side you put on the negative terminal. That way, what we'll be able to do once you have your little battery made is you can clip some wires. So you'll take these little guys, clip one to the copper rod, clip one to the nail. That way you can actually grab hold of these little prongs. Because it doesn't work too well just to kind of like touch them like that. You don't get very good contact. So grab hold of it with a wire, clip them onto these. But that way you'll be able to figure out pretty easily which is the positive positive terminal, which is the negative terminal, and we'll see how much voltage you can make with one. Then what the directions say is we'll put your two cells in series. And then we're gonna try and power some stuff. And I've got a couple things here. I've got some calculators here that I pulled the batteries out of. So these have those little button kind of batteries, so they're here, not in here. So there's no batteries in there, so they won't go on, but instead I connected those little spots with these wires. We'll see if you can actually make the calculator work with your little vinegar batteries. And then I've also got some LEDs. When you're ready for the LEDs, let me know, because I've got some different ones, and I'm not sure which ones will work and which won't. So first couple groups get to test them out to see which ones will actually work, but then we'll try and light up some LEDs. You'll need 2 per set. So I've got two sets per table here, but you guys just have one. So, yep. So I've got plenty for 2 cells per table, but you don't have enough people for 2 because you had a couple people that didn't show up today.
All right.
So you got a question though? Chuck you out there.
I actually can't remember for sure what it was, or if it was an answer. I'll get back to you if I remember.
So this is the rest of what we have on tap for today. So once you get done with this and understand